तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in the last lecture we saw how to use the quantifiers for all of x and there exists x. So, if you have a statement for all of x p of x, then this will imply p of c where c is an arbitrary element of the universe, where c is an arbitrary element of the universe. If you have p of c for some one element, for some c, then this will imply there exists x p of x, because there exists x p of x means for some of x p of x is true. Here c is not an arbitrary element, it can be true for a particular element. If p of c is true for some c, then this will imply there exists x p of x. We have also seen that we cannot interchange the operators, quantifiers, there exists and so on. If you interchange and write like this, it gives a different meaning. This is what we saw in the last lecture by giving some examples. The meaning will be entirely changed. But you can always interchange for all of x, for all of y, to for all of y, for all of x. When both are universal quantifiers, you can interchange the order. Similarly, when both are existential quantifiers also, you can interchange them and use. It does not make a difference. Let us consider how it is true. Consider the set of natural numbers or non-negative integers as the universe, underlying universe. Then universe is the set of non-negative integers. Then look at this statement: for all of x, for all of y, p of xy. Now you can expand it like this. Expanding for all of x, it will be for all of y p of 0y, and for all of y p of 1y, and for all of y p of 2y, and so on. Now this can be expanded as p of 0 0, p of 0 1, you are giving all values for y, p of 0 2 and so on. This can be expanded as p of 1 0, p of 1 1, p of 1 2 and so on. This can be expanded like this and so on. Now the operator AND is commutative and associative, this we have seen earlier. So you can interchange the order in which you have written this P01, P11 etc. You can interchange the order in which they are occurring in the conjunction. Now if you interchange and write, you can write it like this: P00, P10, P20 and so on, P01, P11 etc. That is, you are grouping like this, you are grouping like this, you are grouping like this, you are grouping like this. Now this would represent for all of x, p of x comma 0, and this would represent for all of x, p of x comma 1, and this would represent for all of x, p of x comma 2 and so on. and you have for all of x p of x comma 0, x comma 1, x comma 2 and so on. So, grouping this together you will get for all of y, you will get for all of y, for all of x p of x comma y. So, these are equivalent. Here we have just taken the underlying universe as the set of non-negative integers, it will hold for any other universe also. Now, the same argument you can give for there exists x and there exists y, only thing is you will be using disjunctions, instead of and you will be using or, the symbol or. Again or is commutative and associative, and because of that the same argument you can give changing and into or, and so there exists x, there exists y is equivalent to there exists y, there exists x. Now, let us take some sentences in English and how to write them in the logical notation using quantifiers. Now, before going into that, in arithmetic and all that, you will frequently use something of the form x plus y is equal to y plus x, commutative law, maybe they are for integer arithmetic or Boolean something, x plus y plus z and so on, associative law and so on. What you really mean here is for all of x, for all of y, x plus y is equal to y plus x, and here similarly for all of x, for all of y, for all of z, this statement. But usually when you write the rule, you omit x for all of x, for all of y, for all of z, it is implicitly understood in many cases. Now, let us take some sentences in English and see how they can be written in logical notation using the quantifiers. Let the universe be the set of integers and let n of x denote x is a non-negative integer, e of x denote x is even, o of x denote x is odd, and p of x denote x is prime. Now, let us consider some example. How will you write this statement? There exists an even integer. This will be written as there exists x, e of x. Every integer is even or odd. How will you write this? For all of x, e of x or o of x, even or odd. Then look at this statement, all prime integers are non-negative. How will you transcribe this in logical notation? For all of x, p of x implies n of x. If x is a prime, then it is non-negative. Some more sentences. The only even prime is 2. For all of x, e of x and p of x implies x is equal to 2. This will be transcribed like this. There is one and only one even prime. This can be transcribed as there exists a unique x, e of x and p of x. Because in the last class we saw how to write there exists unique in terms of for all and there exists. Not all integers are odd. This can be written in the form not for all of x, o of x, or there exists x not of o of x. Not all primes are odd. This can be written in the form not for all of x, p of x implies o of x, or it can also be written in the form there exists x, p P of x and not of O of x. There exists a prime which is not odd. This is what it means. Look at this statement. If an integer is not odd, then it is even. This can be written in the form for all of x, not of O of x implies E of x. Of course, if you expand this using the rule for P implies Q can be written in the form not P or Q. So, if you try to write this in that form, it will be for all of x, O of x or E of x, it will become like this. So, every integer is either even or odd, that is what it means. Now, let us consider some more things. Consider this xy is equal to z, denoted by P of xy z. When you bind a variable, it is very important to specify the scope. You have to use parenthesis properly, so that which portion, which quantifier is binding and so on. If you do not use, the meaning may become entirely different and you may write wrong sentences. Now, if xy is equal to x for all y, then x is equal to 0. Taking the underlying inverse should be the set of non-negative integers. If xy is x for all y, that means x should be 0. How will you write this in logical rotation? You will write it like this: for all of x, for all of y, P of xy x implies x is equal to 0. Now, the scope of the quantifier y is this, and the scope of the quantifier x is this whole thing. So, you have to remember that this is the way it has to be written. Now, if you write like this: for all of x, for all of y, P of xy x implies x is equal to 0. This is not correct, because you can have x is equal to 1, y is equal to 1, and then this will satisfy xy is equal to x. Okay. So, there is another value even without x being equal to 0. This could be, I mean this Pyx xy is equal to x can be satisfied. So, this is not a correct statement. This is because you are using, for all of x you are using only this portion, and that is not correct. You cannot write like this also. This is also not correct. This is also not correct. So, you have to use proper the scope. You have to specify the scope. Here the scope of this is this, the scope of it is this. Now, you can also write like this: if xy is not equal to x for some y, then x is not equal to 0. For all of x, there exists y not of P of x comma y comma x implies x not equal to 0. You have to write like this. You can write it x not equal to 0 or not of x is equal to 0, either way. Either way you can write. Now, an expression involving for all of x, p, q like predicate variables, there exists y etc. some quantifiers. This is called a well formed formula of first order logic, or predicate logic, you can say predicate calculus or predicate logic. And a well formed formula of predicate logic is called valid. It is said to be valid if it is true for all universes and all interpretations of predicate variables. If a well-formed formula of predicate logic is true, whatever may be the universe and whatever may be the interpretation you are going to give for the predicate variable, then it is said to be valid. For example, if you take for all of x, p of x implies there exists x p of x, this is always true. Okay, whatever may be p, whatever may be the underlying universe, this is always true, and this is said to be a valid statement in predicate logic. If this some WFF is true for some universe, and some interpretation, it is said to be satisfiable. It is said to be satisfiable. If the WFF is not true for any universe and any interpretation, it is said to be unsatisfiable. You call it as unsatisfiable. So, in predicate logic you have valid expressions, you have satisfiable expression, and you have unsatisfiable expressions. They correspond to tautologies in propositional. Valid corresponds to tautology in propositional logic. This corresponds to a contingency. Sometimes it is true, sometimes it is false, and this corresponds to a contradiction in propositional logic. Now again, coming to the use of this, again the scope is very, very important. There exists x, p of x implies q of x, and there exists x p of x implies there exists x q of x. Are these equivalent or not? Later on we will see that they are not equivalent, but one will imply the other. Okay. So, you cannot just bring in there exists inside the parenthesis like this. Here there exists is outside, the scope of this is this. The scope of this is this, and the scope of this is this. You just cannot use distributive law or something and then bring it inside. Also, when using not, you have to be careful. For example, you may have something like that, not for all of x P of x. What does this mean? This means that it is not true that for all of x P of x is true, is not it? Then that means that there is a value of x for which P of x is not true. Okay. So, you can write it equivalently, like this is equivalent to not that there exists x not of P of x. There is a value for which P of x is not true. So, this not you are bringing inside, and then when you try to bring the not inside, the for all x becomes there exists x. Okay. Now, you can also have some statement like this, not there exists x P of x. This means it is not true that there is a value of x for which P of x is true. What do you mean that by that? For all values of x, P of x is false. So, this is equivalent to saying for all of x not of P of x. So, when you try to bring the not inside, there exists will become for all and for all will become there exists. So, if you have a statement say for all of x, for all of y, there exists z, x plus some P of x, y, z. Okay, write like this. Later on we will take an example. Now, if you want to say not of this, then when you try to bring the not inside, step by step you can bring it inside. This will become there exists x not of for all of y there exists z P of x, y, z, and again when you try to bring it inside, it will become there exists x, there exists y, not there exists z P of x, y, z, and then again when you try to bring it, it will become there exists x, there exists y for all z not of P of x comma y comma z. This is the way you bring not inside the statement. Now, look at this statement, x plus z is equal to y. So, for all of x, for all of y, there exists z, x plus z is equal to y. Now, if you take the underlying universe as a set of integers, this is true. For any value of x and any value of y, you can find a value of z such that x plus z is equal to y. You have to take z to be y minus x, is not it? Now, if you take the underlying universe to be the set of non-negative integers, then this is not true. Okay? This will be true only when y is greater than x. If y is less than x, you cannot find an non-negative integer z such that x plus z is equal to y. That is not for all of x, for all of, this is the correct one. You have x plus z is equal to y. This is should be the statement. But instead of writing this, it is easier to write this way, bringing the not inside. We can write it as there exists x, there exists y for all z, x plus z not equal to y. And this is true because you can choose y, you can choose y less than x, and in that case you cannot find for any value z for which this will be true. Okay. This you can write not equal to or not of x plus z equal to y. This way also you can write. Again the scope is very important, we have to be careful about this. Now, we were considering this example, are they equivalent or not? Before proceeding with that example, let us see for all of x p of x and for all of x q of x. Look at this statement. Is it equivalent to saying for all of x p of x and q of x? Are they equivalent or are they not equivalent? These two are equivalent. Okay. These two are equivalent because suppose you take the underlying universe to be the set of non-negative integers. This one you can write as p0 and p1 and p2 etc. and this you can write as q0 and q1 and etc. Now, when you use and then use commutativity and associativity, you can group like this, and so this is equivalent to this. Now, look at this for all of x p of x or for all of x p q of x and for all of x p of x or q of x. Are they equivalent? They are not equivalent because here means for all of x p of x is true or for all of x q of x is true. Here it means for all of x, for every value of x, either px is true or qx is true. Just look at this way. P of x denote x is even and q of x denote x is odd. So, E of x. In that case, this would mean for all of x, E of x, sorry, this denotes E, this denotes O, say, E of x or O of x. This is true, isn't it? For all, every integer is either even or odd. This is true. But what does this mean? That will mean for all of x, E of x or for all of x, O of x. This is not true. This is true. This is not true. That is, every integer is even or every integer is odd. That is not correct. Okay. So, one may be true, the other may not be true. So, you cannot equate like this. If you have like this, you cannot expand and like this. You use distributivity and expand like this. So, for all distributes over and for all does not distribute over R. Similarly, by a similar argument you can show that there exists x q of x or there exists x p of x if you consider this, and there exists x p of x or q of x. These are equal, they are equivalent. Again by a similar argument like we gave here, instead of this and you will have R here and you can group in this way. Whereas there exists x p of x, there exists x q of x and it p of x and q of x, this will not be equal. So, there exists distributes over R, there exists x does not distribute over and. Now we were considering whether these are equivalent or not. There exists x q of x and there exists x p of x implies q of x. Now this you can write as not of p of x or q of x, and you know that there exists distributes over R. So this you can write as there exists x not p of x or there exists x q of x, and if you take the not outside, there exists will become for all. So not for all of x p of x or there exists x q of x, and essentially this means for all of x p of x implies there exists x q of x. So this is equivalent to this, and whether these two are equivalent, they are not equivalent. Obviously you can see that they are not equivalent. If you try to draw the truth table for this, look at this. For all of x p of x, there exists x p of x, there exists x q of x. Now giving all possible values for this 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0 and so on, you will find that for this, the truth value for all of x p of x implies there exists x q of x is, because the premise is false, all this is true. These two lines of the truth table are not applicable, because when for all of x p of x is true, you cannot have there exists x p of x false. This is not possible. So these two rows of the truth table are not applicable. Now coming to this, again this is true and this is false. So the premise is false and the conclusion is, the premise is true and the conclusion is false. So this is false. Here both of them are true, so this is true. Now if you look at this, again whenever this is 0, this will be true, and it will be false only when this is true and this is false. In these two cases it will be false, rest of the cases it will be true. These two columns are not identical, therefore they are not equivalent, but one will imply the other. Which one will imply the other? See, you can have the antecedent false and the consequence true, that is possible. Okay. So this will imply this will imply the other statement. So we have some logical connectives, logical relationship involving quantifiers. Let us look into them. Now you have this, for all of x, p of x implies p of c, where c is an arbitrary element of the universe. And if you have p of c, for some c, this will imply there exists x p of x. And again this is not is inside, if you take the not outside, for all will become there exists. And then for all of x, p of x will imply there exists p of x. And again in this case, if you take the not outside, there exists will become for all. So there exists x not of p of x is equivalent to saying for all of x, p of x. And here if q does not involve x, whether you bring it inside the bracket or outside the bracket is immaterial. So if q does not involve x, for all of x, p of x and q is equivalent to saying for all of x, p of x and q. Similarly, if q does not involve x, whether you put q inside the parenthesis or outside the parenthesis is immaterial. These two will be equivalent. Again we have seen that for all of x distributes over n. So if you have for all of x, p of x and for all of x, q of x, we can put them within the parenthesis and write for all of x, p of x and q of x. These two are equivalent. Whereas for all does not distribute over R, so this will imply this, they are not equivalent, this will imply this. Similarly, if q does not involve x, and if you use quantifier there exists x, whether you put it within the parenthesis or outside the parenthesis is immaterial, whether you use and or. Here Q does not involve x. So, you get these two statements, and again there exists distributes over R. So, the 13th statement is if you have there exists and R, you can put P of x and Q of x within the parenthesis. Whereas, if you use and, it will not distribute, but there exists x, P of x and Q of x will imply this, but not the other way around. So, these are some of the rules or logical relationship involving quantifiers. Now, generally you may have some statements like this: for all of x, if x is greater than 3, then P of x may hold. You may have statements like this. So, some result may hold for all x greater than 3. You have to write it in this way, but generally you write it in this way: for all of x, x greater than 3, P of x. You write this under this, so that for all values of x greater than 3, this is true. Now, this is a general statement which you might have studied in calculus. The limit of a function as x approaches c is k, which you write as limit as x tends to c f of x is equal to k, if and only for every epsilon greater than 0, there exists delta greater than 0, such that for all of x, if x minus c is less than delta, then f of x minus k is less than epsilon. That is, if you have a function at the value c, the y value is k, if within a short interval near c, the function can take only values which are nearer to k. This is the graphical understanding of this limit. How will you write it in logical notation? You can write it in logical notation like this: for all of x, for all epsilon greater than 0, there exists delta greater than 0, such that for all of x, x minus c less than delta implies f of x minus k is less than epsilon. This is the way you write. Now, when you want to say limit of x minus c f of x is not equal to k, you have to consider the negation of this. So, it will be not for all of x, for all epsilon greater than 0, there exists delta greater than 0 for all of x minus c less than delta implies, and so on. F of x minus k less than delta. Now, if you bring this not inside, this will become there exists epsilon greater than 0 for all delta greater than 0, there exists x, then not of this. Okay. So, this you can write, implication you can write as not of x minus c less than delta, or f of x minus k less than, sorry, this is epsilon, less than epsilon. So, using De Morgan's laws, this will become there exists epsilon greater than 0 for all delta greater than 0, there exists x such that when you bring naught of naught is again double negation, it will be x minus c less than delta, and using De Morgan's laws R will become end. This is naught of f of x minus k less than epsilon. Okay. So, this you will read like this: limit as x tends to c f of x is not equal to k if and only if there is a c greater than 0 such that there is an epsilon greater than 0 such that for every delta greater than 0 there is some x such that x minus c is less than delta, and yet f of x minus k, the difference between them is greater than or equal to epsilon. So, writing it in sentence way, in an English sentence, you have to write it like this. And how do you get this? From this, using negation, and when you bring the naught inside, for all becomes there exists, and there exists becomes for all, again for all becomes there exists, and this naught has come inside. This implication you write in the form not p or q, and then when you bring this inside, it becomes like this, and naught of f of x minus k less than epsilon you can write as f of x minus k, mod of f of x minus k greater than or equal to epsilon. That is, in the figure wise, if the limit is not k, if you take, this is k, if you take a small interval here, then for some value the difference between f of x and k will be more than epsilon. That is what it means. So, such statement we have used several times in logic, but what do they mean using quantifiers? This we want to see now. So, now we see that they have specific meaning when you use quantifiers, and you can express any sentence in mathematics saying a mathematical truth in terms of quantifiers and logical statements. This is called first order logic. Now, let us consider some more examples. Consider this example. We will try to transcribe some English sentences into logical notation using quantifiers. Consider this: let the universe consist of all integers, and let p of x denote x is a prime, q of x denote x is positive, e of x denote x is even, n of x denote x is divisible by 9, s of x denote x is a perfect square, and g of x denote x is greater than 2. Then express each of the following in symbolic form. Let us take some from this and try to write in logical notation. Take the first one: x is even or x is a perfect square. How will you write this in logical notation? X is prime or x is a perfect square, or s of x. P of x denotes x is a prime, s of x denotes x is a perfect square. So, x is even or x is a perfect square is denoted by P of x or s of x. Consider D. If x is a prime, then x is greater than 2. X is a prime is denoted by P of x. X is greater than is 2 is denoted by g of x. So, if x is a prime, then it is greater than 2 is denoted by P of x implies g of x. If then else, if then is denoted by implication. So, if x is a prime, then x is greater than 2 is denoted by p of x implies g of x. This is A. Similarly, you can write for the other 3 B, C and E. Now, let us consider this. Translate each of the following sentences into symbols, first using no existential quantifier and second using no universal quantifier. First one is, not all cars have carburetors. Let car of x denote x is a car. Carbu x denote x has carburetor. Now, the statement is, not all cars have carburetors. Not for all of x, C of x implies car of x implies carbu x. This is the way you write using a universal quantifier. Not all cars have carburetors. Not for all of x, car of x implies carburetor of x, or x is a car implies x has a carburetor. Now, you have written this using universal quantifier only and not existential quantifier. Now, we want to write it using existential quantifier but not universal quantifier. Now, if you try to bring not inside, for all will become there exists. So, this will become there exists not this. That is, there exists x not this implication P implies Q, you can write as not P or Q. So, this you can write as not car of x or car. Now, this not again you can bring inside using De Morgan's laws. So, this will become there exists x, not of car x will become car of x, R will become and using De Morgan's laws and not carbu x. There exists x such that x is a car but it does not have a carburetor. So, the same thing you are expressing using an existential quantifier but not using a universal quantifier. Okay. So, let us consider the next one. No dogs are intelligent. Let dog of x denote x is a dog and intel x denote x is intelligent. The statement is no dogs are intelligent. So, you have to express it using universal quantifier but not existential quantifier, and using existential quantifier and not universal quantifier. So, using universal quantifier alone, this can be written like this: for all of x, dog of x implies not intelligent. X is a dog means it is not intelligent. So, no dogs are intelligent. So, using universal quantifier you can write this way. Now, we have to express this using existential quantifier but not universal quantifier. How can you write it? For all of x, you can introduce two nots here. If you introduce two nots, the effect is nullified. So, this one you can use implication P implies Q can be written as not P or Q. So, not dog of x or not intel of x. 1 naught you can bring outside, 1 naught you can take inside. This 1 naught if you take outside, it will become not there exists x. When you bring the naught this side, for all will become there exists. The other naught you have to bring inside using De Morgan's laws. So, naught of dog of x will be dog of x, and R will become AND using De Morgan's laws, and naught of intel x will become intel x. So, you have to read it this way: not there exists x, dog of x and intelligent x. That is, you do not have something which is a dog and intelligent. So, the same statement you are expressing using universal quantifier but not existential quantifier here, and using existential quantifier but not universal quantifier here. The third statement is some numbers are not real. So, num x denote x is a number, real x denote x is real. So, some numbers are not real. Using existential quantifier you can write it like this: there exists x, num x and not real x. Now, how will you write using universal quantifier? Again same way, you can introduce two knots here, and this one you can write like this. Now, one knot you bring outside, that is not for all of x, one knot you bring inside, not num x or not of real x, that will become real x. And this, if you write using implication, this will become not for all of x, num of x implies real of x. This way you can write. There is a slightly different way also you can write, but we can keep this. The next thing is we shall consider logical inference. You have several theorems, you have systems. You have a system of integer arithmetic where the underlying universe is a set of integers. Then you have rules, you have some axioms. What are the axioms? The axioms are commutative law, associative law, like that, addition, subtraction. Then making use of these axioms and rules of, there are some rules of inference, and making use of those rules of inference, you can deduce some true statements about that system. So, for any system you have some axioms and you have some rules of inference, and starting from axioms and rules of inference, you try to reduce more statements about the system, more true statements about the system, derive more statements about the system. They are called theorems. Theorems are derived from axioms by making use of rules of inference. So, start from axioms, then you will have some more statements, make use of them, apply rules of inference, and ultimately you will arrive at a conclusion which is called a theorem. Okay. Now, an argument goes wrong or a theorem is wrong if you start with wrong axioms, or even if you start with correct axioms, if you use a rule of inference in a wrong manner, then you may arrive at a wrong proof. So, when do you say that a proof is correct? The derivation of the theorem from axioms using rules of inference is called a proof. This is called a proof. You are deriving the proof. And this proof may go wrong if you apply the rules of inference in a wrong manner. Now, we have some rules of inference in logic which we have already seen in the first or the second lecture maybe. From these are the rules. From P you can conclude P or Q, or in the tautological form this implies P implies P or Q. This is called the name of the rule is addition. And if you have P and Q, from this you can conclude P, or in the tautological form this is P and Q implies P, and this rule is called simplification. This is from P and P implies Q, you can conclude Q. From P and P implies Q, you can conclude Q. This is called modus ponens. From not Q and P implies Q, you can conclude not P. From not Q and P and Q, you can conclude not P. This is called modus tollens. Then you have this rule. From P or Q and not P, you conclude Q. This is called disjunctive syllogism. And from P implies Q and Q implies R, you get P implies R. From P implies Q and Q implies R, you have P implies R. This is called hypothetical syllogism. And if you have P and if you have Q, you can conclude P and Q. This is called conjunction. And if you have P implies Q and R implies S, and if you also have P or R, you can conclude Q or S. In the tautological form, this is read as P implies Q and R implies S, and P or R, this will imply Q or S. This rule of inference is called constructive dilemma. And if you have P implies Q and R implies S, and not of this, not of Q and not of S, from this you can conclude not of P or not of R. In the tautological form, it is like this: P implies Q and R implies S, and not Q or not S implies not P or not R. This is called destructive dilemma. And you can see the similarity between this and modus ponens and the similarity between this and modus tollens. These are some rules of inference. And in the next lecture, we shall see some examples where you can find out whether an argument is valid or not by making use of these rules of inferences.